Hi, welcome to Munro Live. I'm Paul Turnbull. We're here today to talk about the Nissan Ariya electric motor. But before I get into the electric motor, I want to give you a little bit of a big picture on the Nissan Ariya itself. Nissan was nice enough to loan us a Nissan Ariya. This particular one is a pre-production prototype, but they're available for sale. This one is doing fantastic in the market. Retail sales for cars have just recently come out, and for EVs, the overall EV market is up about 1.5%, but Nissan is up 25%. And the Nissan Ariya is a big part of the reason why Nissan's up 25% in EV sales. I just want to re-emphasize that the overall EV market is up, not down, even though Tesla is down quite a bit. So but the overall market is, so far this year, up a little bit. That's expected to continue into the third quarter. And then, of course, the fourth quarter, there's going to be a dip due to the expiring of all the incentives. But Cox Automotive suggests that, predicts that overall market is going to end up being flat for EVs for the whole year. So that's where the EV market is in the US. Globally, of course, EVs are up over 30%. A big chunk of that is China, but Europe also, the EVs are up big. So it's only the US where it's relatively flat. Nissan has been in the business for a long time, and they know a thing or two about electric vehicles. Their partner, Renault, in Europe has been doing EVs even longer than Nissan. In particular, Renault has a lot of experience with a special kind of motor, and this motor is an example of that. This is called a Woundfield Synchronous motor. Nissan calls it an externally excited synchronous motor. And the reason they call it that is because the rotor has no magnets. It's instead wound with copper coils, and the copper coils, when you put electricity into the rotor, the copper coils become electromagnets. And so when you make this into an electromagnet, then the rest of the time, then it's controlled very much the same way as a permanent magnet motor is controlled. So you use brushes, good old-fashioned brushes, to put power through the slip ring, just like your alternator in your car today, to energize the coils for the rotor, and then it becomes essentially the same as a permanent magnet motor for the same efficiency, same kind of power density that you get. It's notable that Nissan has done this and made an extremely competitive motor, competitive with the permanent magnet motors out there. So this is a 239 horsepower motor, 178 kilowatts, in a package size and weight that puts it smack dab in the middle of the pack with all of the other permanent magnet motors. So they've achieved a power density that is equal to permanent magnet motor with no magnets. And that completely eliminated for Nissan the issue of supply chain risk. And supply chain risk is a big deal at this moment in time. Nissan anticipated it. They worked with their friends at Renault to come up with a unique and very cost-effective solution that eliminates supply chain risk. So I think a lot of companies right now are looking for this type of a solution to reduce their supply chain risk. And Nissan's way ahead of the game in that respect. So let's just start with the rotor here. So with the rotor, we've got these copper windings that are there are a total of 8 poles. And the copper windings, the issue with a wound field rotor, this thing spins at over 12,000 RPM. And so you have to try to retain the copper windings when it's spinning at very high speed. And so they put these plastic wedges in, and screw them in place, support them with steel on both ends. And they have these two rings as well to help retain the copper windings. So this is a solution that Renault came up with, and Nissan adapted to this 8-pole design. In order to put a bolt all the way through this whole stack, through this plastic wedge, a bolt this thin will tend to stretch. If I just hold it here and I torque down the bolt, then the bolt will tend to stretch and twist, and you won't be able to get reliable clamp load here. And so the trick that they've used is to put a Torx head on the end here so they can support the end and run the nut and bring this in, and they get reliable torque load and clamp load here, stretching the bolt just exactly the right amount so that everything is retained. At Munro, we're not a big fan of threaded fasteners, but if you have to do a threaded fastener, if that's the solution that you've come up with that's best, you need to do it right. And this is an example of a company that does the thread fastener right. They took the time to engineer the thing and not just run a bolt in and run a nut on and say it's done, because then the thing falls apart, and when it's 12,000 RPM and you have nuts falling off, it could be a bad day. So that's the rotor. In order to get the electricity into the rotor, we're going to use a brush holder and brushes. So the brushes, these are carbon brushes, and there's a set of 2 brushes for both the positive and the negative, so for a total of 4 brushes. And they do that to equalize the current across the brushes and minimize brush wear, so that this brush holder is designed to provide enough brush life. Brushes, of course, are a wear item. Enough brush life to last at least 150,000 miles. And the way this is designed, based on my experience with alternators, I'd say this is conservative at 150,000 miles, could very well be a 250,000 miles before they run out of brush wear, and have to replace these brushes. But should something happen, and something unusual is the case, and you end up with having to replace this brush holder or the brushes, then they've made it accessible on the outside of the motor with just this access panel. The brush holder fits in here, and so that it can be replaced easily without dropping the whole transmission. So they can pull it out and put in a new brush holder and service it. So unlikely that it would ever have to be serviced, but you know, when you're handing this vehicle down to your granddaughter, might be nice to put a new set of brushes in. So that's how they managed to get the current into the windings. You can see from the size of the wires here that we aren't talking about hundreds of amps going into the rotor. It's more like tens of amps. So in order to produce the magnetic field, they have enough turns in the coil to get a full strength magnetic field without a lot of current. So these brushes don't have to carry the full power of the electric motor. Instead, the stator carries the full power. So they have a lot of copper for the stator. This stator is wound with a stranded winding. Again, a great choice for Nissan, at least to begin with, because they already had the tooling for this set up. So it's a matter of, again, reducing supply chain risk, reusing existing tooling, minimizing the launch costs, and increasing the likelihood of everything working the first time. And so if you don't have to redo things, that's how you get a successful product launch and make money in the manufacturing business. In order to send that current into the rotor, the inverter has a special circuit to do that. So this inverter has the usual parts, a big capacitor to smooth out the current. This is the control board. It's an Infineon control chip, and it drives the 6 switches that all inverters need to make the synchronous current for the stator. So that goes out the 3 phases. But then there's this additional component that isn't present on most permanent magnet inverters. This component takes the DC power and it PWM, it uses pulse width modulation to send a limited amount of current, a controlled amount of current to the brushes, and then on through the slip ring into the rotor. So this is the field control board, and this is the stator control board. All in, so they can control, that gives this type of motor gives an additional dimension of controllability. So normally a permanent magnet motor, you can't control how strong the magnets are. And so when you're going fast and the rotor is spinning fast, then the voltage generated by the spinning magnets inside your stator is fighting against you and putting the current into the motor. In order to control that, we have to put in what's called field weakening current to put current into the stator, extra current into the stator, in order to control the magnetic field of the rotor. In the case of this, in a Woundfield synchronous motor, instead of putting extra current into the stator, all you have to do to reduce the field is put a little bit less current into the rotor. So at high speed, this type of motor is more efficient than a permanent magnet motor. At low speed, it's the reverse, that because a permanent magnet motor doesn't have to pay the energy cost of putting current into a rotor. The permanent magnet motor is more efficient at low speed. It's at high speed or highway speed where the equation flips, and it flips in favor of this kind of motor. So you tend to get not as good city electric range, but better highway electric range. And Nissan's been in the business long enough to know that it's highway electric range that matters. Everyone cares. Nobody cares about how long you can go in the city because you can just charge, usually at home. Which when you're on the highway from stop to stop, making the calculation of how far I can go before I have to stop, that's when the electric range matters, and that's when this type of motor really shines. So they've done all kinds of little things, subtle things in this motor that show the maturity that Nissan has. Like I said, they've been in the electric motor business, electric vehicle business, longer than anyone, and it shows in the little details that they like to put in, that they put into this motor. It's an oil-cooled motor, which is great because they have to cool the rotor. They're spraying oil on, but they didn't go to extremes to provide extra cooling paths in the stator because the duty cycle doesn't demand it for a vehicle like this. And so they kept it simple. And they're reusing the same stuff that they've learned from previous designs. That's a consistent theme through this whole motor. Reusing great ideas that they've had, and if it's not broke, don't fix it. And they have another example of that in the drivetrain, where a typical drivetrain has an ordinary amount of maybe a little better friction than most. But one of the things that they added is park pawl. This is a device that locks in when you put the motor into park to keep the vehicle steady. It's in every single automatic transmission. And it's just actuated with this little electric actuator. They make these by the million, and it's in all their automatic transmissions. They just carried it over into the electric vehicle. We see most electric vehicles omit this part, And then they rely on the anti-lock brake mechanism to engage to keep the car stationary when you're in park. That's a cost save, but it's a risk, a potential risk. And so this vehicle kind of has the belt and suspenders approach, the tried and true park pawl, plus the, if all else fails, automatic anti-lock brakes. So that's part of the philosophy that Nissan uses, that if it's not broke, don't fix it. Put the park pawl in. It's what we have in every automatic transmission. People are used to how it behaves, and it gives us an extra degree of safety. That's the part of the philosophy. They've done a few other things that show their maturity on electric motors and electric vehicles. This type of system, especially when you're putting pulse width modulated DC current into the rotor, the possibility of voltages in the rotor and the voltages coming through and needing to find a ground path become significant. And so we would like that those ground paths not be through the bearings. If the rotor becomes electrified and it grounds through the bearings, then that produces little lightning bolts that jump across to the ball bearings and can leave little potholes in the races. And the potholes eventually become ridges, like a road becoming a washboarded road. And that can lead to an annoying noise and eventually destroy the bearing. So we'd like to not have that electric current flowing through the bearings. So what they do is they've added a little brush. This brush engages the secondary shaft here, and that brush helps dissipate any built up electric charge and keeps the currents low, and it grounds it straight to the housing so that there's a path for electricity. This is the kind of thing that a company that has experience with this kind of machine just puts into their system without thinking too much of it. The other thing I thought was cute is all these motors, they're sealed, of course. They are filled with oil, but a seal can't be perfect. And so you have a breather to make sure that the pressure inside the housing is equalized with the pressure outside, so you don't get oil leaks and that sort of thing. The only trouble is that when you do something like drive through a big puddle and you have to ford through like 30 inches of water, the housing can suddenly cool and the air can suddenly cool, and that can pull a vacuum and suck air or water into the system, into the drive unit, which you'd like to not have. And so they, instead of just putting a breather on, this is actually a snorkel to bring the height of the air intake high enough that this vehicle would be able to ford through 30 inches of water and just drive right along without the motor being interrupted at all. So little things, subtle details, some of them add cost, but all of them eliminate worries for the end customer. And that's the kind of a sign of a vehicle team that has been working on these kinds of vehicles for quite a while. There are a handful of other parts that I didn't really mention here. I'll just quickly go through. This part here is a resolver, and that's to emphasize that this is a synchronous motor. In order to control it, in order to control the switches and make torque, we have to know exactly the location of the magnets with respect to the stator, and we do that using a resolver. We've got an oil pump and this oil heat exchanger. The oil goes into these paths and circulates inside, and water coolant goes through these paths and circulates inside separate layers. And that way the heat from the windings and the other components in the motor end up getting out to the water coolant, the radiator, where it can be dissipated. So this is the setup for the Nissan Ariya Woundfield synchronous motor, or they call it externally excited synchronous motor. And it's exciting to see because it's an opportunity to make a very competitive motor, both cost and size and power, without any magnets, to eliminate the supply chain risk. I'm sure that a lot of companies are looking at doing something very much like this for their upcoming designs. So Nissan's way ahead in that respect. So thank you for joining us today on Munro Live, and hope to see you next time. If you're interested in motor reports, motors like this, we have a history of motor reports from throughout the industry available on our website. And so just stop by and have a look.